Okay, y'all, let's get started today. Remember, we have a coding portion of the final tomorrow in lab. There will be 3 coding questions, one on recursion, one on trees that could very well involve recursion, and then one on linked list data structures that will require you to do pointer manipulation. You'll have the full 2 hours to complete the lab. You'll have or be allowed a 1-page cheat sheet front and back, which you will hand in before you leave. Any questions about what will be happening? It'll be all on Code Assessor. There is practice materials up, including a practice Code Assessor problem. If you go to the website and you go to the exams part, you'll see that there's some prepping for final, and there's a whole bunch of different suggested things that you can do. The practice Code Assessor question is probably the best thing to review for the code problem tomorrow. The remaining materials are good for the in-class final that will be held on Thursday, April 30th, in here from 8 to 10. That one will be worth 70 points. Tomorrow's exam will be worth 50, and it will not involve coding on the in-class exam on that Thursday. So all the coding will be done tomorrow. For the in-class exam on April 30th, the paper portion, you will not be allowed a cheat sheet. That will be a closed note, closed book exam. So it will just be in format like the second midterm. Questions about any of that? Okay. The material on the final will include what we're going over today with BTrees, and it will include big O notation, which we may or may not start today, but which we for sure will be going over on Thursday. So today we'll be finishing up BTrees. We're not going to go through the code itself, but we're going to make sure you understand the insertion and the deletion and the find algorithms at a conceptual level. The code's pretty involved, and I don't think it's all that interesting to look at. Whereas, for example, for the AVL trees, looking at the AVL, the rotations and the way they do the balancing, I think that is interesting to see how that code gets implemented. Okay, so you'll remember that last time we said that, let's see if we can get that with BTrees, we had 2 types. We had BTrees and B+ trees. And the idea was that they are kind of like extensions of balanced binary search trees, except that instead of being limited to 2 nodes, they are limited to having m children. So if we have a tree of order m, then it can have at most m children, per node, and minimally must have m divided by 2, the ceiling of that. Okay, and that condition guarantees us a certain occupancy in each node. It guarantees that every node has at least m divided by 2 children, and therefore it guarantees that Okay, so this minimal, this guarantees that find, insert, and delete all take log n time. But in this case, instead of log 2, it's log m divided by 2 times. So it's even faster than order log 2 because the ceiling, if m is, say, 100, that's log 50 of n, which is even smaller, in fact, fairly significantly smaller than log 2 of n. So it reduces significantly the number of levels in your tree. Okay? So there's a couple other things just reviewing quickly. So we require that, or not require, but the root is the only node that may contain fewer than m divided by 2 children. So the root may contain as few as 2 children. In fact, if it's a leaf node, it might have no children. Okay, that would be pretty unusual to have a tree that small. Okay, and then a B plus tree, the difference between, does anyone remember the difference between a B tree and a B plus tree?
B plus tree only has values at the leaves.
Very good. So a B plus tree, so a B tree stores values at interior nodes, whereas B plus trees only store values at the leaves. And that gives B plus trees a higher order. They're able to store more keys in each node, and therefore M is bigger for B plus trees. So the implication of this is that B plus trees, this implies that B plus trees have a higher value for M. Which means they have fewer levels. And at the end, we'll review why that is important. Won't do that for the time being. In fact, for the time being, we're going to talk about B trees. Okay, so that's the basic aspect of B trees. So if we go to the notes, the first kind of algorithm, let's see if we can't get something a little more interesting. There we go. So if we're going to try to find the key in a B tree, the algorithm is very similar to the find algorithm for a binary search tree. So first of all, we keep the keys in sorted order in the node. So in the diagram that you see here, if you look at each node, the keys are sorted in each of the nodes. And so when I try to find, one other thing that was important is that if you look at any keys, quote, left and right subtrees, you have the requirement that all keys in we'll say, a key's left subtree, are less than the key, which in turn is less than all keys in a key's right subtree. So that's a guarantee as well. So for example, if we look at Q, we see in fact that all the keys in its so-called left subtree, which is this subtree, are less than Q, and all of the keys in its so-called right subtree are greater than Q. And the same thing holds for T. Everything in its left subtree is less than it, and everything in its right subtree is greater than it. So the find algorithm is very similar to what we did with a binary search tree. So we start at the root, which in this case has a single key. So let's say that we're looking for K. Okay, so we start, and in this case we ask, is K less than M? And it is, so we're going to go to the left subtree because we know that any key, that in order that all keys in the left subtree are less than M, therefore K must be in the left subtree if it exists. So now we end up at this subtree right here, and we simply do a linear search through the tree until we find a key that is greater than K. So here, whoops, so our find algorithm is essentially while key not found and node not a leaf, or not, we'll say not null. So those are the two conditions. Then find first key, call it K1 in node, such that, which I'm abbreviating ST, key is less than K1. Okay? And then set node equals left pointer for K1. Okay, and if we find K, so obviously if we find, and also we say break if key equals, so break if key equals K1. So that's kind of pseudocode for our find. Now you'll see immediately that there seems to be a bit of a problem here, because is K ever less than any of the keys in this node right here? Is it ever less than that? No. So K ends up being greater than G. So it's the one exception if you get to the very end of the node and you haven't found any key that is greater than the one we're searching for, then you follow that tree's right subtree. So in this case, we will end up following the right subtree for G, and we find by doing a linear search through this particular leaf that K is in that leaf. Okay, so we find the first key K1 in node such that K is less than K1 and set node equal to the left pointer for it. and there's kind of a bit of a, let's erase this. Okay. If key is greater than all keys in node, then node equals right pointer for last key in the node. And I can't write it all out because I won't get space on this slide, but it's if the key is greater than all keys in the node, then the node equals the right pointer for the last key in the node. I just can't write, well, here we go, for the last key in the node. So that's the situation here. Okay, so if we were to do the same thing, except that now we're looking for, let's say, S. Okay, S is greater than M, so we're going to go here. S is not less than Q, but S is less than T, so we follow this one, and we end up with S. So find, fairly simple. Any questions about it? Okay. In that case, we'll move on to insert, which is more interesting and also more difficult. Okay, so insert, in fact, this goes through a whole chain of things. So it's kind of nice to just follow along. So initially, you're just inserting into the root. So let's say that we have a B tree of order 5. So the notes are assuming that we have a B tree of order 5. So we have 5 children, meaning we have a maximum of m-1 keys. So a corollary is that each node has a maximum of m-1, or in this case, 4 keys. So in this case, we start, and the first 4 keys that we insert are the keys C, N, G, and A. So basically, we are going to insert this set of keys right there. Okay, so the first 4 keys are C, N, G, and A. They get inserted. We put them in sorted order, but the initial root node can hold 4 keys, so we simply, for the first 4, do an insert. The first interesting action occurs when we insert H. I'm sorry. The first interesting one is when we insert H. When we insert H, it's going to overflow the node. It can't hold a 5th key. So what we do in that case is we promote the middle key. So in effect, we put the key in there in sorted order, which would be A, C, G, H, N. Now we can't actually do that because the node's not big enough to accommodate 5 keys. But conceptually, that's what we do. Then we promote the middle element, which is G, and split the node into 2, with the lower half of the keys going into the left node and the upper half of the keys going into the right node. Now in practice, half the keys will stay in the existing node and half the keys will move to a new node. And in this case, because there was no parent, we also had to create a new root node. So in this case, you can see we created a new root node and put G into that new root node. And then, as you can see, A and C went over here, H and N went over there. So questions about that insertion? Okay. So you may want to write down this sequence because I do not have it. I'm going to have to move off of this page, or you may want to follow along on your own computer. But the next key that we're going to, you can just quickly see that next we insert E, and E will go right here. Then we insert K, and K will go right here. Then we insert Q, Q goes here. And now we insert M, and based on what we've just said, take a moment and think about what happens when we insert M. So right now, we have this situation. And we're about to insert M. So think about what you think happens when I insert M based on what happened when I inserted H. What do you think is going to happen?
You're going to create a new parent now.
You do. So first kind of conceptually work through it the way I did. So what's the first thing I did? Yep, I inserted M, so it was in sorted order. Okay. What's the next thing I do?
Promote M.
I promote M. Very good. And now I split the node in two. So I get H and K in one node, and I get N and Q in the other node. Okay, so that becomes my new tree. Okay, if we just slide this up, there, whoops, here it is, right there. Okay, so that's right here, same thing that I've drawn right here. Okay, so now they insert F, W, L, and T, and F, W, L, and T, as you can see, just further fill up this particular tree. So now Z gets added. Think for a moment what the tree is going to look like after Z gets added. Okay, this is exactly what I'm likely to ask you on the exam. So it's important that you understand how to do these inserts. Okay, so I'm inserting Z. Okay, I'm going to ask, sorry, I forget your name. Yep. Alex?
Yeah.
Okay, so what are we going to do, Alex? Pardon? We're inserting Z. So we're adding Z to this tree right here. Okay. And very good. And we split, so now W and Z end up together, and N and Q end up together. Okay, so we end up with this right here. Okay, so let's see if I can't get them both on the same slide. There we go. So if we insert Z, it comes out at the end of here. T moves up. We have N and Q here, W and Z here. We're all good. Okay, and finally, we'll get to do a bunch more, and we get down to this tree here, and we're going to add S. Okay, think about what happens when we add S to this tree right here. So here's our tree S. Whoops, no, here's our tree, and we're going to add S. Okay, way in the back of the room, Stephen. Okay, just, pardon? Okay, so it doesn't actually go to the right of R, because if you look at S, whoops, take it, you're right, sorry, better than me. So you do. S is less than T, so you go here and you add it to the right of R. Okay, so next step, promote Q. Okay, and that's going to, let's see if they come up with a temporary tree. Nope. So Q gets promoted, and we have a split where we have R and S in one tree and N and P in the other. I know this is getting a little hard to read, but what do you think we do now? Very good. We promote M, splitting it like that. So we essentially get a tree where M is by itself with D and G as one child and Q and T as the other child. So let me put the 2 here. So you can see M did get promoted, like Stephen said, and DG and QT. DG and Q was promoted. And then remember that NP and RS became the 2 children of Q. Okay, so here's RS and here's NP, and they're both children of Q. Okay, there is a nice site that if you want some practice, we'll give it to you. It is, bet I can't get this much larger. I will send around the link later, but it is www.cs.usfca.edu /Gallus visualization / capital B capital T REE.html. And if you go to that site, it will allow you to experiment with finding these various, with the 3 operations. So we're about to do delete, but if you, again, I will post this to Piazza, so if you don't get this down right now, about to remove it. But you can see we'll do some insertions. So we'll do, this time numbers, we'll insert 100, 50, 80, 70, and 6, well, it's a little slow, 60, 40, okay, 120. So you can see what it's doing is you do each insertion, it's showing you where it's going and doing whatever it needs to do. So if we insert 65, you can predict that 65 is going to go down to this one. It's going to split the node, and 100 should be promoted. And you can see it does it. Now it does it pretty fast. I wish it would do it more slowly, and I wish it had some controls that allowed you to figure out what's going on, but it's still better than nothing. So now if we try to find 70, you can see it starts, it's very fast, but at least you get some idea of what's going on. Okay, and it's certainly, if you want practice preparing for the final, it's a good way to get practice. Okay, so any questions about insert? Okay, so we'll move on to delete, which is a bit more complicated. Okay, so delete is pretty easy if we are deleting from a leaf node, and the leaf node has more than the minimum number of children. Okay, so let's say we want to delete H from this tree right here. No problemo. The reason it's not a problem is because we're allowed to have, well, let's go over it. So we're deleting H, okay? And if you remember, in a tree of order M, we are allowed to have a minimum of M divided by 2 ceiling -1 keys in a node. So a minimum of M divided by 2 -1 keys in a node. Because it can have a minimum of, you might be saying, wait a minute, but it's a minimum of M divided by 2 children. Okay, so there's going to be 1 fewer keys. So in this case, when we delete, we have a B tree of order 5. And therefore, the minimum number of keys is equal to the ceiling of 5 divided by 2 minus 1, which is equal to 3 minus 1, which is equal to 2. So we're allowed to have a minimum of 2 keys in a node. So if we delete H from the tree, that simply reduces the size of that leaf to 2 keys, and that exceeds the minimum. So that's the easy case. Okay, the easy case, in fact, the most common case is that we're deleting a key from the leaf and that there are far more keys in the leaf than the minimum number. Okay, so that's the easy case. So we deleted H. Let's select a harder case. Okay, so next, let's say that we delete T. Okay, so let's delete T. Well, T is in an interior node. Okay, so what we do is we find its successor in ascending order, and its successor is going to be in its right subtree. Okay, so that successor is W. So what we do is we delete W from the leaf and promote it to the interior node. Now in this case, that's great because the leaf has more than enough keys to accommodate the deletion. Okay, so this is another pretty easy case. We delete from an interior node, and the node below it, the leaf node, has more than enough keys to accommodate it. So another easy case. Okay, before I go on though, I'm just going to show you that the visualization does it slightly differently. So let's insert a few more keys. 160 and 180 and 200. And I need a few more, so keep putting in some. 150. Okay, So I am going to delete 160 out of here. I know, unfortunately, let's see if I can make this bigger. There we, well, unfortunately what's making bigger is, maybe, can you read this in the back? Kind of, no. Can you read that? It's the best I can do. So I'll push it down. So now I'm going to delete 160, and you're going to see that actually, I believe this visualization is going to pull 150 up. It doesn't matter, in fact, whether you pull the predecessor or the immediate successor. So I'm going to pull 160, and it pulled 150 up. So it actually doesn't matter whether you pull the successor or the predecessor. Okay? Because I want you to do the successor just like the notes have it. But I'm just warning you in advance that if you practice with this visualization, it uses the predecessor rather than the successor. What's important is you understand the difference, because otherwise they're just mere operations. They're just mere operations. Okay? But just so you know it, the visualization site is pulling the predecessor up, whereas the notes that we're looking at, the written notes, are pulling the successor up. Okay, so after deleting T and bringing up W, we have this tree right here. Okay, so now they're going to come up with, whoops, here we go, the case where we delete R. So if this is going to be a harder case. If we delete R, what's the problem?
You only have one key left.
You have only one key left, and that's less than the minimum. Okay, so we're deleting R, and what we do in this case is we look to see if either sibling is able to take it on. There's two siblings here, NP and XYP. And we're going to see if the sibling can take on the extra keys. Okay? So in this case, either node could take it. Okay, both nodes have room. Arbitrarily, the notes are choosing to move it over to the right-hand one. Okay? There's a reason for that. I'll show you in a moment. But just for a moment, we move S over, and it joins X, Y, and Z. Okay, so S comes over here. Whoops. R's gone. But you can see we now have only two children, right? And yet, whoops, no, that's not what I wanted. Don't care about my system center protection. So I have two keys right there. Okay, so what happens is that we also bring W down. Okay, so W moves down into this node as well, creating SXWYZ. And so now we have the node SXW, whoops, is that right? Actually, W doesn't have to move down. I take it back. Wait, yes it does. Arg. Let me just look at the answer for a second. Ah, that was my mistake. Okay, backing up. I got ahead of myself and missed one of the cases. Okay, backing up. I was wrong in what I did. So, R gets deleted. We borrow, not borrow, we take from a sibling that's able to give us one. So our rightmost sibling can give us one, our leftmost sibling cannot, because our leftmost sibling is already minimal. Okay, so our left sibling cannot spare a key, but our right sibling can spare a key. So we take the first key out of the right sibling and give it to the left sibling. So now it becomes S and X, and this becomes Y and Z. Okay? Now, what would seem to be our problem here? Just a second. What's the problem? Yes.
W and X.
W and X, because X is greater than W, right? So we shouldn't have W. We have a problem, which is if W comes there, then, I'm sorry, not that. We have an issue that with W still coming out here, X is in the left subtree right here, and that's no good. Okay, so what we're going to do, show the final result, is we're going to take X up and move W down. And that's going to solve our problem. Okay, so rather than moving X over like that, instead X moves up and W moves down. And that's going to solve the problem. So it's kind of like moving, it's pushing the, it's not really a rotation either. But X gets promoted and W comes down. And that's going to ensure that we keep our ordering in place. Okay, so this one's worth writing down. Okay, so the case is deletion from a leaf that causes the leaf to have too few keys. So the first and best case is that a sibling, one of the two siblings, can spare a key. So case one is one of the siblings can spare a key. Okay, so we'll assume it is the rightmost one. So if the rightmost one can spare it, so right sibling can spare it. So we'll say right sibling can spare K1. Okay, so what we do is promote K1 to the interior node. Or to the parent. So we'll say to the parent. And then 2, we demote a key in the parent to the leaf with the deleted key. Okay, and it's not just any key in the parent, it was the key that pointed to the right sibling. So when I say a key, what I'm really talking about is demoting the key that points to that right sibling. Okay, so questions about that? Everyone got that down? Okay. So let's say that, let's just change this tree slightly. So let's say that what we had in P, there's nothing MN, let's say we had down here N, O, and P. And let's say that X was not in the tree. And again, we need to delete R. Okay, so now the left sibling can spare the key, but the right sibling can't, right? So we delete R. So what we can do now, what do you think we do now? Over there. Have a crack.
Sorry, I wasn't looking.
Okay. Scott, how do you do it? It happens. What do we do if we delete R and NOP is bigger? Throw it open to the room. Yes.
We can move P up
P up, that's right,
and Q down.
and Q down. Very good. So it's the same operation except that now we're moving the rightmost element from the left child over, and then we're moving the key from the parent down. Does that make sense? Okay, so that's the mirror case. I'm not going to write it down because it's just the mirror case. Okay, so the next one to delete is going to be a real doozy. We're going to delete E. Okay, and the problem here is that neither sibling is able to spare a key. Okay, neither sibling can spare a key. So in this case, we actually have to do a combination. That's what I meant earlier when I said I skipped a case. Now we're at the situation where we have to combine. Okay, so in this case, arbitrarily, we're going to combine these two nodes. And when we combine those two nodes, we're going to go from having 3 children up there to having only 2 children. Right? So we have to also move down the key that used to point to, quote, those 2 siblings, we moved down the key whose left and right siblings are getting merged, which in this case is D. So D comes down to there. Okay, so now we have a node that is ACDF, and up here we are again temporarily short. Okay, we've had the same problem, which is there's not enough keys in this interior node. We do the same thing at the interior node that we did at the leaf, which is we look and see, is there a sibling that could spare a key? Well, unfortunately, there is no sibling that can spare a key. This is the only sibling, and it has itself only 2 keys. So again, we have to combine these 2 nodes. Okay, and when we combine them, just as before, M has to come down. So we end up with a tree that has a single node here, G, M, Q, and X. Okay, so G, so let's just kind of work it all out. So this was the intermediate situation after we deleted E, we moved D down, so we came up with this situation. Okay, now we had to move M down. Okay, we move M down, and you can see that there's 1, 2, 3, 4, 5 children left. So when we move M down into here, we're going to end up with M pointing to what two nodes? What nodes will M point to? So we're moving M down.
KL and N.
Very good. So it points here, and it points there. Okay, which if we look on the next slide, there we go. As Gerald said, M points on the left subtree to K and L, and on the right subtree it points to N and P. Okay? So that's the hardest case of all. Questions about it? I'll write down the pseudocode. Okay, so let's write down the pseudocode for that one. So thus far we've seen a number of cases. So delete from a B tree. The first case was the easiest, where we delete from a leaf that has more than the required, that has more than the minimum number of keys. Okay, so that was case one. And we simply delete it. In that case, we deleted the key from the leaf and we're done. Okay. Second case that we considered was we delete from an interior node and it has, I'll say, a child that has more than the required number of keys. Okay, in that case what we do is we remove a key from the child and promote it to the interior node. Okay, so if we remove the key from the right child, so there's two cases again, okay, remove the smallest key from a right child or if it's the left child that we're removing from, we remove the largest key. Okay, now we haven't looked at a certain case yet, which is the case when we looked at it was that the interior node was sitting right above a leaf. We haven't yet looked at the case where that interior node is sitting above another interior node. Okay, so we will have to consider that case. We haven't gotten to that case yet. Okay, the next case we considered, have you got this? Steven, see, did you get it? You still writing? You got it? Okay. Okay, so the third case was we delete from a leaf that has the minimum number of keys. Okay, and we saw that case A was one of the two siblings can spare a key. Okay, and I went through this case, so I'm going to abbreviate it, but in this case we move a key from the sibling. Actually, we promote. So we'll assume arbitrarily. So let's say the right sibling, if right sibling. Then we promote leftmost key in right sibling to interior node, and we demote the key that points to the leaf and the right sibling to the leaf. And we do the same thing if it's a left sibling, but if it's a left sibling, we promote the rightmost key in the left sibling. Okay? So moving on, case 4. Whoops, that's not case 4. This is case actually B. So case B is no sibling can spare a key. So if no sibling can spare a key, we have to merge this leaf with one of the two siblings. So merge leaf with one of its two siblings. And demote from the interior node, from the parent, the key that points to these two children. Okay, and then if necessary, recursively do this merging further up the tree. So if needed, repeat delete process on parent node. Okay, so that may have to be done recursively because the parent may also not be able to spare a key. It may be at the minimum. So if the parent's at the minimum, you're going to have to do something with the parent. Okay, so questions about this? Okay, let's do, in that case, keep working through our examples. So here's another tree, and we're going to delete C from it. Okay, so what is the, whoops, let's get down here. If we delete C, what is typically the first thing that we would do? Yes, Samantha. See if the child can spare one. So we're going to see if this child, typically what we would do is we would promote D. Okay? Or if it couldn't spare one, but the left one could spare one, then we would promote B. But we have an issue, which is neither leaf can spare one. Okay? So neither leaf can spare one. If we do, we get this situation right here. So we promote it D, we delete it C, promote it D. We have a empty, not an empty, but a leaf that has too few keys. Okay, so we now just apply the normal deletion. It's as though we deleted D, so we treat it just as though we deleted D from here. So what's the situation when we delete a key from a leaf and there's no sibling that can handle it, that can spare a key? Samantha, I'll let you see if you can continue. So neither sibling can spare a key. Yep, so we can merge with either one. Very good. So we can merge either way. So we'll merge A, B, and E. Okay, so we do our merger. And when we merge A, B, and E, we have to demote D. So we end up with A, B, D, E like that. Okay, but this is the case now where we have to do a recursive check on the parent because the parent is got a single key and we can't allow that. So what do you think we do here? Pardon? What do you want to do? Promote D? D? B. You want to promote B. Okay, so that's a good try at it, but in fact, not quite correct, Ardelan. Sarah? Okay. If we promote E, it's so we don't promote E either. We could try that, but the problem is if we promote it, okay, so if we promote it E or B, so in both cases, Sarah and Ardelan, I'll throw it open to both of you. what would you do after the promotion? So you would promote, and Ardalan would promote F, and Sarah, you would promote E. But you don't have enough children for them. I guess the issue is you don't have enough children. Okay, but we can pull the same trick we did with the leaves, which is we go over to our sibling and say, brother, can you spare a key? Okay, and why, yes, it can spare M. So we move M, except we don't move it over here. We do the same trick that we did with the leaves, which is we move M up to here, and we move J down to here. Okay, so M gets promoted up to here, J comes down, forming two nodes, and we redistribute our pointers. Okay, so this pointer comes over here. Okay, so if we go and look, we see that's what happened. So M came up. You can see M came up to the root. J, which you barely can't see, J came down to here. And now this child right here moved over and became a child over out of this one. Whoops. Okay, so if you look down here at KL, KL is now pointed to out of there. Yes.
Why did KL move?
Okay.
It wouldn't fit over on the other side.
So KL, so the question is, why did KL move? So it had to move because when M got deleted here, whoops, now we can only accommodate 3 children. If we have 2 keys, we can only point to 3 children. So it had to move because we can't accommodate, with only 2 keys, we can't accommodate 4 children anymore. Plus, with M moving up to here, we had to make sure that with M moving up, remember K and L is less than M, right? If it stayed in the right subtree, it would be greater than M, which would violate our B tree condition. So it also has to move over to the left subtree because it's less than M. Okay, so when you delete a key out of the interior node, you have to also do this movement of the one of the children. Okay, I don't claim this is easy. Okay, but the general principle is there that anytime you, with any node, when it loses a key, it basically sees whether it can borrow from its siblings. If it can borrow from a sibling, then you move the key from the sibling up and you demote a key from the parent. And then if it's an interior node, you may have to redistribute a child. Okay, and if it doesn't have, if a sibling can't spare a key, then you have to merge 2 nodes together and demote a key from the parent. I think that may be the last, yep, that's the last example that they give. Okay, but let's see if I can. Okay, so the last example, this is always good. So we got a couple minutes. See if you can figure out what happens if you delete M, the root, from this tray. Okay, so take a moment and figure out if you can, what happens when you delete M. Actually, this is going to take too long. I'm going to leave that as a homework exercise. It's going to take about 6 or 7 minutes to explain what's going to go on. So, as a homework exercise, we'll discuss it on Thursday, and then we'll get into big O notation. But see if you can figure out what happens if M gets deleted from this tree. And we'll talk about it on Thursday, as well as talking about big O notation on Thursday. Remember, your last lab is due this evening, partially because if you wait it, you might have some issues with tomorrow's coding problem, although I will tell you in advance, tomorrow's coding problems are link structures, recursion, and an operation on a binary tree. It is not an operation that has to deal with an AVL tree. So if you're studying for tomorrow, don't worry about AVL trees. Worry about binary search trees.